Okay, so first of all, I wanted to thank the organizers for inviting me to this really, really interesting activity and being part of it. This morning has been very interesting to me. Like, this is the first time in my life that I'm at a conference that it's only about black holes and there's data. It's like super, super exciting. However, I'm going to break that pattern. I have absolutely zero plots to show to you, and this is going to be extremely theoretical. But I'll talk about black holes. So black holes are at the center of this talk, and I'll tell you what we're thinking about and how we're thinking about black holes in this very, very theoretical aspect. So I love black holes because they're super easy to draw. Black circle, there you go. Okay? I tried to be a little bit creative, give it a little bit of texture, but that's just because it was way too easy to just draw a black circle. But that's it, that's a black hole. Now the aspect of black holes that I'm really interested in is their thermodynamic nature. So Hawking, Bardeen, Carter, Bekenstein, and many others in the mid-70s established that there was a really, really interesting relationship between the properties of the black holes and thermodynamic quantities. And the main result out of this analogy is that a black hole is an object that carries entropy. Its entropy is proportional to the area of the event horizon, so if you want the border of the circle, divided by 4 times g Newton. So in some sense, basically half of my time, instead of thinking of black holes as a black circle, I can think of it as a cup of tea, okay? So I like to think of black holes as a thermodynamic object that carries lots of entropy, and it has a temperature associated to it, okay? Now, along those lines, the statement that you can make is basically the following. Gravity, hence it's a theory, general relativity is a theory that knows about thermodynamics. And the follow-up question that you ask after that is saying, well, if that's the case, then quantum gravity should know about statistical mechanics, okay? And so in principle, I should be able to write down this entropy as the logarithm of some microstates, okay? And this is the type of question that my talk is going to focus on and trying to understand if we can make sense of this equality, okay? Now, for those of you that don't know, secretly or not so secretly, I'm a string theorist, and inside of string theory, we can provide examples of this equality, okay? And what's interesting about that framework, the framework that string theory gives us, is that it comes with a lot of extra information as well. So the leading piece that I wrote in the previous slide is this area law, but there's also a various amounts of corrections that come from the gravitational side, if you watch this side of the equation, and there's also a bunch of corrections that will come as a prediction once you give me a microscopic system that will account for this entropy, a statistical system. Now, the story of trying to understand this equality in string theory, it's a very long story, and it actually has its origins around here. So the early troublemakers in this arena, the people that gave the first example of how to make sense of this equality is Andy, who's here in the audience, and Kumru Bafa, which is also at Harvard. And there's after that, so this happened in '95, and after that there was a whole explosion in the field of trying to understand better this equality, trying to understand this formula, what does it imply, and so forth. And if I were to list everybody and everything that has happened since then, I would spend the rest of my 15 minutes just listing names of people, so I won't do that, but I do want to highlight one other very important character in this story, and this will be based a lot on the equations and the formulas that I'm going to derive, and this is Ashok Sen. So a lot of the contributions, particularly the interpretation and the reproducing these corrections that I was discussing, are due to his work and by his collaborators, okay? So these are basically 3 main characters in the story. Now, when we're inside of string theory, there's basically 2 important features that I think that are key to take into account of why this program was successful. Why were these gentlemen able to understand this equality? So the 2 aspects, in my opinion, that are very important is one that goes under the name of holography. I'm not going to explain what holography is because I'm not going to use it very heavily, but what I basically want to advocate is that we have a framework nowadays how to understand quantum gravity and how to understand black holes. And within this framework, it's very natural to think that the entropy of a black hole scales with its area instead of its volume, as one would have expected. And the other aspect that made for a lot of progress and a lot of interesting results was the fact that a lot of the systems are supersymmetric. And that, as a theorist, gives us a lot of control. So we can at least take some step further in trying to answer these challenging questions. And so what I'm going to do now is basically grab what I learned from these papers, which is now, by nowadays, textbook material. And what I'll try to do is understand how can I go away from that specificity, okay? So the examples that we know are very, very specific, and that sometimes is seen as a bug. What I want to do today is show you that that's actually a feature, and I'll try to expand out of there, okay? So the focus for the next 10 minutes will be in trying to understand how can we build classes of statistical systems which have the right features to describe black hole physics, okay? So in some sense, this talk, it's about black holes, but it's also about partition functions. It's about statistical mechanics, okay? So I want to be able to build objects that are the microscopic degrees of freedom and say this is actually has the same physics and the same features that you would attribute to a black hole, okay? So because likely I'm going to run out of time and Andy's going to be harassing me, the strategy that we're going to take is as follows. So what you have to keep in mind, what happens throughout this talk are basically the 4 following steps. I'm exploiting, and I'm finding inspiration on the known examples that have been built in string theory, okay? So that's how we're basically making progress. We're like studying those cases and then saying, okay, how can we move away from that point? I'm going to make use a lot of symmetries. I'm going to exploit symmetries a lot, so it will look like I'm putting myself in a corner. As a theorist, I try to make things as simple as I can so that I can have analytical control in the system. I'm also going to secretly be exploiting holography. So if you don't see it, don't worry, but if there's experts in the audience and you want to know how much am I exploiting it, please ask me afterwards. And the new feature that we're bringing and the results that we developed recently is that we're also abusing mathematicians. So I want to build these statistical systems, and in number theory, these guys are really good at building this type of partition functions, and I'm basically going to use results known in that literature and put them in a physical context, okay? And in a black hole context in particular. So, okay, so let me first, I'm going to go first through the gravitational side of things and tell you something about the black holes. And then we're going to move into how would I use that knowledge to build the statistics, okay? So the extremal black hole. So here, everybody's very familiar with a black hole. A black hole is characterized by a mass, a charge, and an angular momentum. And basically, a way you can think of a black hole is that, okay, so if you're very far away, the geometry is very flat. It's asymptotically, basically Minkowski, empty space, and you're in your rocket ship, and then one day you decide to go into the black hole. Okay, so here I draw the horizon, like sort of, okay, you go in, something happens. But this journey will take you some finite amount of time. You'll get there. You'll get to the horizon, and you'll cross it. Now, an extremal black hole is a case where you start tuning these parameters such that the time, okay, such that the time that it takes you to get to the horizon is basically infinite. So you kind of never get there. What that buys you is that you can forget about the fact this very, very, very long throat gives you the capacity of forgetting what happens far away. So I don't want the distractions of flat space and things that are messy and Minkowski. I just want to focus on the black hole and its horizon because its entropy was controlled by that data. So I don't want to get distracted by physics far away from the black hole. Now in GR, the way people define these solutions is by saying that if it's a solution that has multiple horizons, extremal black holes is when they coincide. And the enhancement of symmetries that I was advocating before tells me basically that this long throat becomes something that is called ADS, a space with negative curvature. They can also be supersymmetric, so I can even add more symmetries to the system. But one thing that is very interesting is that as you take the extremal limit, the temperature goes to 0. And you might have thought by the laws of thermodynamics that the entropy also had to go to 0. However, there's a huge amount of entropy at the end of the day, a huge amount of residual entropy. And this is when, as a theorist, you have just conservation of difficulty. So I put myself in a corner trying to make things as simple as I could in terms of the equations and how they look like. But I have now the challenge of finding statistical systems that when I take them to 0 temperature, they have tons of entropy. And that's not generic. Okay? So that's my challenge. Now, for the equations, just very briefly, for those of you that wanted to know exactly what type of backgrounds I'm looking at, this throat geometry is basically described by this type of metric. For sake of concreteness, I'm going to focus on black holes that have electric and magnetic charges. So here I wrote down what the field strengths that support that geometry. And the geometry itself has some curvature, radius, and they depend on these electric charges. And then the area of the horizon is a function of that parameter. Okay? So the area basically is controlled by how much electric and magnetic charge you have. Now I want to understand the entropy of the solution. And Ashok Sen basically gave a very systematic method on how to compute the leading term, but also its corrections. And it's based on what's known as the quantum entropy function. You don't need to know the details about that, but I just wanted to point out there's a way how we define the entropy with its corrections. And when you take the low energy limit of this equation, you get the formula that you're accustomed to, the area correction. But something else that I want to highlight is that there's another piece, a sub-leading piece that is as well universal or robust from the gravitational side. And it comes with a coefficient. And so as you look at what happens at low energies, you get the area law that it's very known, and then you get this extra correction here, which in the gravitational side is controlled by the massless particles. And this formula, the dot, dot, dots, mean that I'm ignoring terms as I take this very large area limit. So the challenge is to find the statistical systems. The opportunity is that once I give you a candidate for a statistical system, there's not just an area law that I have to reproduce, there's also a sub-leading correction that should be reproducible, among other corrections as well, but I just want to focus on those two. Okay, so now the extreme measures. So how am I going to build the systems? So as I said, I'm going to find inspiration in string theory. So let me flash to you again. I'm bragging here. So this is roughly, very, very crudely, what's known about certain classes of black holes. So here, basically, I'm tabulating a bunch of different theories that people consider, the number of dimensions, how many supersymmetries they have. All of them have this leading piece that is the area divided by 4. And then these are the logarithmic corrections that I was discussing. And the check marks here basically indicate when there's a microscopic model and when we're capable of reproducing these results quite correctly. So this is a table that Ashok has reported on in various reviews. Okay, so this is basically what we know. So based on that, let's make some progress. So my first input is that I'm going to look for the statistical systems, and I'm going to make the decision to look to statistical systems in 1+1 dimensions. And I'm looking for these very highly degenerate systems. Now, what is my justification to do this? Well, my justification is because this is basically the check marks in that list previously do have an origin of a 1+1 dimensional CFT. And holography is also kind of, this is where I'm secretly using it as an inspiration. And I have 1 minute left. So let me go through this quickly. So now if I use this holographic principle, I'm going to start translating basically the quantities of the black hole to quantities in the CFT. So in the CFT, I will have a central charge, I will have an energy, I will have some other quantum numbers, it doesn't matter, but there's basically a map between the quantities in the statistical system and the quantities in the black hole. And the claim is that then, if I compute the number of states in this field theory, I should be able to reproduce the entropy of the black hole. Now, the reason why this is not a very easy problem to do is that the regime that I'm interested in is when the area is very big. And this basically, if you look at how the holographic dictionary goes, it tells you that the energies have to be roughly comparable to the central charges, generically. And not any of these 1+1 systems are going to satisfy those requirements, okay? So this is not a universal behavior in the land of these conformal field theories, okay? So trying to find a huge amount of entropy in this regime, it also goes very closely related to what in our community people are denoting nowadays, this sparseness condition on the spectrum. So I need more data, okay? This is not enough. So my second input is to do the following. I'm going to average over theories, okay? So I'm trying to look for typicality. I'm trying to look for typicality in this land of field theories. And when we try to do typicality, we use methods of statistical physics. And so what I'm going to do is try to find what is the typicality among these theories, okay? So I'm going to do that. And this will create a new type of generating functional. And on top of, I'm not going to look at generic generating functionals. I'm going to look at generating functionals that are called Siegel-modular forms. I'll tell you in a second what that means. Why? Because it gives me what I want, okay? So I'll be successful. And in the negative 30 seconds that I have. And it also, this type of symmetry, it was really key in the known examples that people have studied in the past. Okay? So this is what I'm doing here. So I'm basically, I will grab some partition function, and here I'm averaging over the central charge. So this degeneracy that I'm trying to compute, I'm not just summing over energies or other quantum numbers, I'm also averaging over central charges. And I'm going to try to identify partition functions that have this type of behavior, okay? Now, there's the Siegel-modular form here, just so you know, just focus on this. Basically, they're this type of generating functionals that are invariant under an exchange symmetry between the two parameters here. So that's all I'm going to say because I don't have more time. And then I just want to say, here's where I'm stealing from the mathematicians. So the mathematicians have very beautiful ways how to build these functions with very, very, very little input. So basically, you just give me what they will call a seed, one type of partition function, and then they will tell you what is a family of these Siegel-modular forms, and we can extract all the information that we want. So I'm almost done. Here I'm just showing basically some examples of functions that have the behaviors that I want. Okay, and these are not examples that were previously studied in the literature known to string theory. So these types of functions have a very big growth. So here basically we study how these functions behave in various different regimes, and we looked at the leading behavior. So there's going to be an area growth. And then we also looked at the logarithmic behavior of these functions. And there's a big amount of entropy in what we will call this regime of interest when E was very similar to C. So, okay. I just threw up a bunch of stuff at you, so sorry. It's hard to do 15 minutes. Well, now I'm 17, sorry. So just as an outlook, I narrowed it down to two things, okay? So I'm just going to say two things. Basically, what we have achieved recently is to build new examples of statistical systems that have black hole-like features. The challenge, and what I'm not showing you right here in this slide, is that I just showed you partition functions in this super fast way. But what we don't know is what is its gravitational or string theory interpretation. So it's a kind of awkward position to be in, that I first give you the partition function and then I'm going to give you the theory. But okay, that's what I have. It's they're very explicit functions, so I don't think it's a problem. So here I'll end, and as a credit, these are the people, my collaborators that have been helping me in doing this type of work. So thank you very much.
Okay, we have time for a few questions. Eric?
So you mentioned studying the typicality of these. It's not clear to me in this context what that means. It's a theorem that there's no non-trivial Borel measure on an infinite dimensional Fauché space or Fauché manifold. And I said it's a theorem that there's no non-trivial Borel measure on an infinite dimensional Fauché manifold, which is what you're dealing with here. So it's not clear to me but typicality is characterized by measures. So it's not clear to me what one means by typicality here.
I'm not summing over all theories. I'm not sure, I don't think. So the type of generating functionals that I'm looking at, so when I average over theories, it's a class, it's a family of theories, if you wish. So I'm not averaging over everything. So there is a well-defined measure from that point of view.
It's finite dimensional?
No, it doesn't have to be finite dimensional. Like Hilbert spaces are not finite dimensional.
And they have no non-trivial Borel measure, infinite dimensional
But I
Hilbert
can
spaces.
still do StatMech. That doesn't, I still have a thermodynamic limit, and I can quantify thermodynamic quantities, even if the Hilbert space is infinite dimensional. So that's not a problem in this point of view. So defining partition functions, when the energy is infinitely big, yes, you have to regulate, you will have to do some regularization procedure and stuff, and you have to understand what's happening in those regions, but it's not a problem from this point of view. So we can talk a bit more about it later, but it's not the obstruction.
You got a question? No.
I can have a question. Oh. So at some point in the slide you flashed, you seem to be summing over theories of different central charge.
Yeah.
So what would this mean from the gravitational side? Would it have something to do with these laws of thermodynamics where you vary the cosmological constant?
Yeah, that's interesting because it might, well, roughly speaking, that's what you're doing because the central charge is basically governing the cosmological constant on the other side. Here I'm not, from the gravitational side, I'm not using it that way. I'm using it from the statistical point of view as a trick to try to access what we call the large C or the large N limit, okay? So, because basically I need to understand how this degeneracy behaves when the central charge is very big, and so I'm using it just as a mathematical artifact. How do I access that? So the partition functions in general in StatMech are designed for the same thing. You want to know how the system behaves at very high energies, and what you do is build this partition function that sums over energies, and then you understand yeah. So, but it does make you think about the fact that it was so easy to do it this way. It does make you think about if in holography we should be thinking in holography as oh, is this the right way how to treat the dictionary and to define certain observables and to get access to them more broadly? And that, I don't know. It works very well here, but yeah.
I think maybe we better, okay, Avi, yeah.
Just a quick question. So you showed the expansion in the first order correction, alpha times ln, the area. And I was wondering, in black hole evaporation, there is this issue of whether there is a remnant when the black hole evaporates, or does it evaporate to zero? Now, if it evaporates to zero mass, then this small correction is not small anymore because the ln of a small area relative to Newton's constant is not a small number. Yeah. And so what does the theory say about that when you take the area to zero?
Oh, that's... Sorry, that's a tough question. So for yeah. So there's a sense in which I can define the law. So first of all, one of the reasons why I took the zero temperature limit is because there I think I have more control in trying to define this for a large range of parameters because I don't have Hawking evaporation. So I'm at zero temperature, so it's kind of a special point from that point of view. Now, if at finite temperature, I can define this log, but it's only approximate in the sense that when you do the computation, you're thinking that you're putting the black hole in a box and that you're trying to make it not evaporate in some sense. So it is a very delicate object, and what its full quantum definition, at least in my opinion, is not extremely clear. So I don't know how to interpret and I don't know what's going to happen to this type of corrections as the black hole evaporates and I get the remnant. So yeah, I'm putting myself in this corner where I think that I can make sense of the equality and these corrections are meaningful. But yeah, that's a very good question.
Okay, first of all, let me thank the organizers for the opportunity to be part of this exciting conference. My topic today will be BMS current algebras, and so the first part of the talk should be for everybody. So this will be about BMS symmetry and especially BMS current algebras. And the second part will be a bit more speculative, and it will be about the central charge that you can see at null infinity. So most of this is based on work done in collaboration with Cédric Troussard. Okay. Recently at a conference in King's College, I learned that the Bondi mass loss formula was extremely important for people in the end of the 50s and the beginning of the 60s to convince them that gravitational wave actually existed. And this is because this formula is a true nonlinear effect of general relativity, and it tells you that when a system emits gravitational waves, it loses mass as a consequence, when an isolated system does that. Okay. So the setup that I'm going to consider is the following setup. So you are at null infinity, and you start at a given moment of retarded time, and then you look what happens when you move forward in retarded time. And there is gravitational radiation leaking out of the system. Now, a lot of the recent progress here has been to understand what happens when you try to link what happens at past null infinity, but this forces you to really understand what happens at spatial infinity. This is a complicated problem. This is a much simpler problem and an older problem, but still it might have some relevance as it could be directly connected to what you can observe. So on the technical side, what I'm going to use is, or what is always used in this context, is to use complex coordinates on the celestial sphere at Scri+, and they make the metric on the sphere conformally flat. So if you're interested in conservation laws and you deal with systems that derive from an action principle, the conservation laws are of course intimately connected to symmetries. And the relevant symmetries in this context are asymptotic symmetries at null infinity. And the good news is that in order to learn about them, all you have to do is to read this 1962 paper by Ray Sachs, in which you can find everything already. So the point is that in the presence of gravitational radiation, the symmetry group is no longer the Poincaré group, but it is a larger group, which is called the BMS group. When you work at the level of the algebra, you have basically two choices for the enhancement of the symmetry algebra. So the standard GR choice is that you are interested in having globally well-defined quantities, everything well-defined on the sphere. And in that case, your Lorentz transformation arise on Scri as globally well-defined conformal killing vectors of the metric of the sphere. Okay. And the second thing then, because you want everything to be globally well-defined, is that, so this Lorentz generator acts in a semi-direct way on angle-dependent translations, the so-called super-translations, and in this way, in order to have everything globally well-defined, you expand them in terms of spherical harmonics. Another choice that is more close to people doing CFT is to do expansions that allow for poles in your expansion. So you really do an expansion of your generators in terms of Laurent series, and then you find as the symmetry algebra 2 copies of the centerless Virasoro algebra. And again, they act in a semi-direct way on super translations that now you also have to expand in terms of Laurent series. In this way, the Poincaré subalgebra arises as the lowest modes of this infinite-dimensional algebra. So building conserved quantities in general relativity is notoriously difficult, but what I can say here is that when the dust settles, you find that the time component of the BMS currents are just given by the Bondi mass and angular momentum aspects, suitably multiplied by the BMS generator. So this F is a combination of BMS translations and rotations, if you want, and this Y's, they are, if you want, the rotations or the super rotations. And you can see that this formula for the BMS currents has both a linear piece and a nonlinear piece. So the linear piece involves components, asymptotic components of the wild tensor, and this piece is, for instance, if you're interested in the mass of the Kerr black hole or the angular momentum of the Kerr black hole, you get them from these linear pieces. These nonlinear pieces, they are related to the asymptotic part of the shear and to the news, and you can show that they are directly related to the transverse traces polarizations of the gravitational waves. Then you have to work out how your symmetries act on the fields. And when you do this computation, what you find is that in this transformation there are interesting inhomogeneous terms that have been, a lot of physics has been gotten recently out of this inhomogeneous transformation laws, because one way to interpret them is to say that the Minkowski vacuum, which corresponds to having sigma and sigma dot being 0, breaks BMS invariance, and then you have interesting physics that happens. The formula that I would like to sell you today is the formula for current algebra. So what you are doing is, because you want a local formula that works for both versions of the BMS algebra, you work out the time component, but also the spatial components of the currents, and then you act with the symmetry associated to one set of BMS generators on the current associated with another BMS generator. And the terms that you might have expected are the terms which are underlined in red, because if you are allowed to integrate, this is just going to say that the currents form a representation of your symmetries, which is what you expect in a standard theory. Here, what you are going to see is that there are two kinds of breakings. So the first breaking here on the left-hand side is a breaking that is due to the gravitational, to the news leaving the system. So this breaking is here. It's intimately connected to the non-integrability of the gravitational charges found by Wald and Zupas. And then there's another term, which, as I'm going to try to convince you in the second part of the talk, is the central extension that we heard in the previous talk, but at null infinity. So this part vanishes, for instance, if you're not interested in superrotations or in poles. If you're only interested in globally well-defined objects, this part vanishes. So out of this formula for current algebra, when you stick in for one of the generators the retarded time translation generator, the formula just reduces to a formula telling you by how much the given BMS currents are not conserved. So the breaking here is again due to the news and due to the superrotations. So if you're not allowing for poles and you are allowed and you can really integrate over the sphere, then you can build the BMS charges, and the integral just kills these spatial boundary terms, and you get the formula for the non-conservation of the BMS charges. The Bondi mass loss formula, which was the starting point of the discussion here, you get if you use for Xi the time translation generator, and then you find that Bondi mass loss is expressed by this expression, and you see, for instance, from the formula directly that the mass loss is always positive. So let me now move to the part of the talk where I'm interested in this central extension. So usually when you have such unexpected terms, they can teach you something important about the system. So for instance, central extensions in the Galilean algebra have been found by Bachmann. They are related to the mass in non-relativistic theories. The central extension that turns the Witt algebra into the Virasoro algebra has, of course, many important applications. There is the gravitational analog of that. But here the analogy that I want to make is the analogy, and this is for a technical reason, with anomalies in quantum field theory. So if you study non-abelian Yang-Mills theory, the Adler-Badin gauge anomaly satisfies an important consistency condition. It's a condition that relates the characteristic class, or a suitable characteristic class, to the primitive element of the Lie algebra, and the Adler-Badin anomaly sits exactly here, so it satisfies this consistency condition just from the way it is defined. And here you can do the same. You can assemble this field-dependent central charge into a suitable 2 form. You promote your Lie algebra elements to suitable fermionic generators, and then you find that this field-dependent central charge or central extension satisfies exactly a similar consistency condition to the one that you have here. When studying more exotic gauge theories than Yang-Mills theories or gravitational theories, one finds that the commutator of gauge symmetries sometimes does not close with structure constants, but with structure functions. And at the same time, when you see these structure functions, the Jacobi identity becomes more complicated. So in the Jacobi identity, there are additional terms that take into account this dependence of the structure functions on the fields. So it turns out that if you want to build a central extension in a Lie algebra, you have to control the appropriate cohomology class. It's the second cohomology class that you have to control. And in this case, it turns out that the cohomology operator that controls the central extensions in the presence of field dependence is exactly the consistency condition that we have seen on the previous slide. So it turns out that you can build in the same way that you can build a centrally extended Lie algebra, you can build a centrally extended object here in the case where everything depends on the fields, if you have a solution to this consistency condition here. And having a solution to this consistency condition requires you to drop all boundary terms in all spatial boundary terms. So these spatial boundary terms can be dropped if you are not integrating over the sphere, and this you can no longer do in a naive way because you have put poles on your sphere, but you have to integrate like you integrate in conformal field theory. So your integral has to be so you expand everything in terms of series in zeta and zeta bar, and you have to take the residues separately in zeta and zeta bar to have a well-defined integral, and this integral is known to kill these spatial boundary terms. When you do that, you get definite numbers for this central charge at infinity, and the numbers that you get depend on the asymptotic part of the shear, on the modes of the asymptotic part of the shear. Okay, why are we interested in this structure? Of course, we are interested in these structures, which are, well, except for their mathematical interest, we are interested in them because of the fascinating derivation that has been done of the Bekenstein-Hawking entropy of the three-dimensional BTZ black hole by using Cardy formula. So we would like to do something similar here for the black hole from the viewpoint of null infinity instead of what is more often done from the viewpoint of a near horizon analysis. But the problem is that the asymptotic part of the shear is actually 0 for the Kerr black hole. But this is true if you compute the Kerr black hole and you take this surface to be a sphere or even the Riemann sphere at infinity. But from these infinitesimal formulas that I have shown you, you can actually compute how the asymptotic part of the shear transforms when you map the Riemann sphere or the punctured Riemann sphere to the cylinder. If you do this kind of mapping, which is completely standard in conformal field theory, then you find that the asymptotic part of the shear gets a finite shift, so you get a number for the Kerr black hole, and that this shift is proportional to the retarded time. Then, of course, you have to understand that if you are Euclidean, maybe this becomes a factor of inverse temperature, but if you really can use this to say something about the entropy of the Kerr black hole, is very much work in progress. So this is what we are working on, and I have not much more to say on this. So let me maybe conclude by saying that I think studying asymptotically flat spacetimes at null infinity contains a lot of beautiful mathematical structures, and I hope what is also, of course, very exciting is that these mathematical structures have the potential to be of direct physical relevance. Okay, thank you.
Okay, thank you. Questions? Yes, Castro?
You said that the field-dependent central charge depends on the shear asymptotic. So this just physically would correspond to saying that this central charge, let's say you turn on superrotation and then you consider these central extensions, would depend on the polarization of the gravitational waves or something like that?
Of course, also like that, but also for the Kerr black hole itself, as I tried to show you, you get also a finite number if you do a finite size effect and if you map Scry to a cylinder. What that really means is not completely clear to me, but both things are true. So you could get, if you have a solution which has the right modes of the shear, then you also have a number. That's what I'm trying to say. But you also get a number for Kerr by the standard thing of putting things on the cylinder. In fact.
Hi, is anything known about the Bondi mass loss formula and the generating vector field and so on if you have the scry which is space-like, let's say with the cosmological constant strictly greater than 0?
So you are saying if scry is space-like?
Yes, for Einstein's equations with lambda 0, greater than 0.
I think that's an interesting question. So people are studying this. For instance, people are now trying to understand in the context of ADS-CFT, in the presence, well, of the cosmological constant, how Robinson-Trautmann waves, because you can also define them in ADS, how would you see them or their energy properties at infinity? So it's not clear, not completely clear to me what the status of that is, but the solutions, in fact, are very close to the solutions in flat space. They are almost the same. So but somehow you have to maybe do different boundary conditions to understand what is going on at this boundary. So I think it's a question which is really being studied, but I'm not an expert on that.
I see. Okay, no problem. Thank you.
Okay, I just would like to make a quick comment on this. There's been a lot of progress in the last several decades by relativists in constructing solutions of spinning black holes pulled by strings. And they have these beautiful analytic solutions. Maybe you've seen them. And I believe that in that context, scry does exactly what you want it to. It becomes a cylinder, so maybe that would be relevant. Okay. Yes, scry becomes a cylinder.
Oh, okay, so I really need to look that up.
Yes.
Well, and also there's the solutions that you have discussed in your papers with Sasha, which is these impulsive gravitational waves, which have a chance of having the right sigma, for instance.
We didn't do the spinning black hole in there, but it's in the literature. People have found the exact solutions, so maybe that would be relevant.
So it is in the reference to your paper with Sasha?
I don't know. There's been some beautiful progress on these spinnings. What is the guy's name? I forget. I can find it for you. All right, we should go on to the next one. Thank you very much.
Okay, thank you very much. And it's my great honor to be here. I am interested in proving mathematical theorems that provide results towards the resolution of the fully nonlinear black hole stability conjecture and the strong cosmic censorship. So in order to address any of these conjectures, one needs to understand the dynamics of black holes, and in particular to understand the asymptotics of the evolution of scalar fields on black hole spacetimes. So there has been a lot of purely mathematical works in the past 10 or 15 so years on this problem. It will be impossible for me to give you a sketch of what has been done, but what I would like to do is to I would like to focus on the importance of conservation laws along characteristic hypersurfaces for the evolution of scalar fields. So I will explain in a moment what I mean by conservation laws. But I want to convince that such conservation laws determine the evolution of scalar fields in the future. Okay, so the models of interest will be massless scalar fields on sub-extremal black holes and their late time asymptotics, and we will also have scalar fields on extremal black holes. So we'll study sub-extremal and extremal black holes. And again, the motivation is the black hole stability problem and the strong cosmic sensors. Okay, this is the introductory slide. So why do I care about the massless scalar fields? If we write the Einstein equations in harmonic gates, then we see that they take a form of nonlinear wave equations. So since the Einstein equations themselves are of hyperbolic character and they take precisely a nonlinear wave form, it makes sense to consider as a toy model the behavior of the wave equation on black hole backgrounds. So the goal is to consider the massless wave equation on black holes, consider initial data, and try to understand what the scalar field and all its derivatives do, how they behave asymptotically in time. The goal is to prove upper bounds, which will allow us to deduce that perturbations disperse. So this is important for stability considerations. And at the same time, it's also important to provide lower bounds, because we need some strength for the perturbation to be preserved throughout time, hoping that these lower bounds will allow us to prove that in the interior, the massless fields, the fields amplify. And so you get some instabilities and singularities, which leads to the resolution of the strong cosmic censorship. So it's important that we obtain upper and lower bounds. And that's why I'm interested in the exact asymptotics, which in some sense provide both of these things. And again, the emphasis in my talk will be on conservation laws. So what do I mean by conservation laws along null hypersurfaces? I simply mean that we consider a foliation with spheres of a null hypersurface. And conservation law in this case corresponds to integrals which are defined on each of these sections of our null hypersurface, and they are conserved. They are independent of the section that we choose. And the conservation law holds for all solutions to the wave equation. So here we have a function f that depends on the geometry of the sections of our null hypersurface, and also it depends on the solutions and all its derivatives of the scalar field. So what we want is these integrals to be independent of V, independent of the section that we choose, for all solutions to the wave equation. Okay, equivalently, we can understand conservation laws along characteristic hypersurfaces as being, as the existence of closed-to forms that depend on scalar fields. Because we simply integrate this closed-to form, the derivative of this to form, and we get the conservation at the boundary spheres. Okay, so let me explain to you now why okay, let's first talk with the submaximal case. So the main question that one wants to understand is what the expected decay rate, right, for solutions to the wave equation on black holes. So consider here the Schwarzschild case, more generally the Kerr case, the Eisen-Nordstrom, and so on. Okay, so we all know that in the case of Minkowski, we have strong Hawkins principle. So if we consider compactly supported fields, then the asymptotics are trivial. There is no tail. In the case of black hole spacetimes, this is not true. You can consider you can consider compactly supported fields, but which are supported in time for all times. In fact, Price, 40 years ago approximately, derived the exact, heuristically provided the exact tails, and he proved that the tails will be inverse polynomial. The tail depends on the spherical harmonic frequency, and if we consider the full solution, which would correspond for L equal to 0, then the leading order asymptotic would be 1 over T to the 3. Okay. So there has been a lot of work in the physics and the mathematical literature understanding related questions. However, there has been no rigorous proof on point-wise lower bounds. It was not known if scalar fields indeed can decay slower than 1 over T to the 3. And also, there had not been any mathematical rigorous work on deriving the exact late time asymptotics. So we have results on the decay rates, but we didn't have results on the exact asymptotics for the scalar fields. There has been in the physics literature a lot of work with by taking the Laplace transform and doing works using quasi-normal modes and trying to derive the leading order asymptotics, but they have not been understood properly. So what I want to convince you now is that a kind of conservation law that we have on all black hole spacetimes, which is on all asymptotically flat spacetimes, which is the one given by the Newman-Penrose constant, is what determines the leading order asymptotics for the evolution. Okay, so let's recall what the Newman-Penrose constant is. So along the null infinity of any asymptotically flat spacetime, we have a conservation law which consists of the integral over the spatial sections of null infinity of an appropriately rescaled transversal derivative of the radiation field at null infinity. So R squared is a radius, dV is a transversal derivative to null infinity. It's an outgoing null derivative, and RPC is an appropriate weight rescaled field. So this integral does not depend on what section we choose to integrate over on null infinity. However, why do I care? How can I have that this quantity determines the evolution of a scalar field of a black hole? On a black hole, precisely in the case that we consider compactly supported initial data, because in this case, if we consider compactly supported initial data, then initially, you know that this Newman-Penrose constant will be 0 because the scalar field is 0 in the neighborhood of the null infinity initially. So why having that the quantity is conserved but it's 0 will give me asymptotics, which will lead to something non-trivial, such as this decay rates. So the answer is that it's not the Newman-Penrose constant of the scalar field itself that will give us the asymptotics of the scalar field itself. But we need to look at something else. So what we need to do is the following. First, let me tell you the following. If we have the scalar field psi, then it has some decay. If I take the t derivative, where t is a stationary killing field derivative of psi, then we expect more decay. If I take 2 time derivatives, then I expect even more decay. Now, since I want to understand the exact asymptotics, I would like somehow to have things that decay as slowly as possible. So instead of adding extra derivatives to the scalar field, I will just remove 1 t derivative. So if you associate to scalar field psi another solution to the wave equation that has a property that each t derivative is the original scalar field, then you obtain simply this scalar field here, which is obtained by inverting the t operator, the dt operator. So the inverse dt of psi is a new solution to the wave equation that has a property that its t derivative is our original scalar field. Now, the property in general of such a new scalar field is that the Newman-Penrose constant of this new solution is generically non-zero, even though the original scalar field psi was compactly supported, so its Newman-Penrose constant was 0. So the Newman-Penrose constant of this new associated solution can be explicitly computed using the initial data of the original psi. And what we obtained recently with Angelopoulos, who is at UCLA, and Gajic, who is at Imperial in London, is the following precise leading order asymptotics of psi. So psi decays indeed as 1 over t to the 3, and the leading order asymptotic is exactly 1 over t to the 3, and the coefficient, the exact coefficient, is that Newman-Penrose constant of this associated new scalar field that I mentioned earlier. So the asymptotics along any constant R hypersurface, including the event horizon, the asymptotics along any hypersurface, time-like hypersurface of the scalar field is uniquely determined by the Newman-Penrose constant of an associated scalar field. Associated scalar field. As I said before, you can compute the Newman-Penrose constant in terms of the initial data of psi, and the computation, for example, on the t equals 0 hypersurface on a Schwarzschild space-time is the one that I have written here. So you can see that the integral, it's an integral along the initial hypersurface that only contains the t derivative of psi. And for example, this result recovers the fact that if you start with a scalar field which is time symmetric, that is to say the initial data are such that the time derivative is 0, then you obtain more decay. So this is immediately obtained by this result because if the t derivative of psi is 0, then the Newman-Penrose constant of this associated scalar field is 0, which gives us extra decay for psi from the above asymptotics. Okay. So this is the first indication that conservation laws on Lang hypersurfaces dominate the asymptotics of scalar fields. So the asymptotics of the radiation field on null infinity are again given in terms of the same quantity. It's the Newman-Penrose constant of the associated scalar field. It's just that the decay rate is, of course, 1 over t to the 3 to the 2, not 1 over t to the 3 as before. But again, the leading order asymptotic is dominated, it's governed by the same quantity, which is a conserved quantity. So let's just make a remark here. The asymptotics along null infinity are given by twice this Newman-Penrose constant, whereas the asymptotics along the event horizon are given by -8 times this Newman-Penrose constant. So these asymptotics suggest that there is a very strong correlation between the evolution of the scalar field along the event horizon and the evolution of the scalar field along null infinity. Okay? And this correlation is given precisely in terms of this quantity, the Newman-Penrose constant of this expression. This also recovers another very well-known result in scattering theory that says that if you consider arbitrary polynomially decaying, inverse polynomially decaying data along the event horizon and null infinity, and you try to solve backwards by using scattering theory, then you will obtain a singular solution. That is to say, you cannot prescribe any scattering data you want on the event horizon, null infinity, and solve backwards and obtain something regular. And indeed, this is demonstrated here, precisely in view of the strong correlation that the data should have on null infinity and the event horizon, so that they arise from a forward in time regular solution. Okay, so this is what I wanted to say about sub-extremal black holes. Now we can talk about extremal black holes. So in the case of extremal black holes, we have the Newman-Penrose constant on the event, on null infinity, but we also have a new conserved charge exactly on the event horizon. So if we consider, for example, extremal as a Nordstrom, then the integral over any section of an expression which is ypc plus 1 over 2 mpc is conserved. It doesn't depend on what section you choose. So m is the mass, and ypc is a transversal derivative to the event horizon. And it's time translation transversal derivative, so y doesn't carry any weights. Okay, so we have a new conservation law on the extremal event horizon. So we have two conservation laws in the extremal case. We have one on the event horizon, one on null infinity. Now, what is the results that we have for the asymptotics in this case? So in this case, the asymptotics along the event horizon of the scalar field are much lower. They are not 1 over t to the 3. The leading order term is 1 over 2, 1 over tau. And the term that dominates this, governs this asymptotic, is the conserved quantity that I just showed you earlier. So the asymptotics in the extremal case along the event horizon are now dominated by the conserved quantity along the event, on the event horizon. So it doesn't matter what the Newman-Penrose constant of psi or any associated quantity to psi is. It just what matters is what is the conserved quantity along the event horizon. Okay, so as you can see in the extremal case, we have a much lower decay rate. So that suggests that you must have some instability because the decay rate is lower. So indeed, we can see the instability if we look at derivatives of the scalar field. So if we consider the ypc derivative, which is again a time translation transversal derivative or vector field to the event horizon, then the ypc derivative along the event horizon does not decay, and in fact converges to this conserved quantity that generically will be non-zero. Whereas the second transversal derivative, the ypc, point-wise along the event horizon, asymptotically blows up. So this is in stark contrast with the sub-extremal case, where all these quantities decay and with sufficiently fast polynomial rates. And this blow-up results that I just mentioned are on the event horizon. So what happens slightly away from the horizon? So the instability persists even slightly away from the horizon in an L2 sense, in the sense that if we integrate the energy, then you still get something which is infinity. And this is very bad from a mathematical point of view if you try to prove stability results, because you have point-wise growth, but also L2 growth, energy growth. So that basically tells you that it's very bad from an instability point of view. Okay, this instability was discovered a few years ago and has been since studied by various people. But I don't have time, of course, to mention most of these works. But what I would like to say is that, okay, what I said is about for the linear scalar field. are these instabilities relevant in the nonlinear theory? And a very beautiful work by the group of Real at Cambridge is the following. So they considered perturbations of the Einstein-Maxwell scalar field system in the context of the Einstein-Maxwell scalar field system. They consider perturbations of extremal Rising Nostrum, and they prove that the maximal development of these perturbed spacetimes diverge from the original extremal Rising Nostrum in the future. So their results are consistent with the instabilities that I showed you earlier, because they obtain that various quantities along the event horizon do not decay, as is the case here for y psi, and in fact, higher order derivatives blow up. So you have derivatives of curvature blowing up asymptotically along the event horizon if you consider perturbations of extremal Rising Nostrum. And this is a genuine result about nonlinear stability of the extremal black holes. Okay, these are numerical simulations, and we'll be very interested to turn this into proper mathematical theorems. Another result that I wanted to mention about extremal black holes, which is now not related to conserved quantities, but I would like to mention because it's recent and very beautiful, is the following. So the results here that I mentioned are for wave solutions to the wave equation on extremal Rising Nostrum. These results also hold for axisymmetric solutions on extremal Kerr. So axisymmetric solutions on extremal Kerr, we know exactly what they do. They behave as it's in this slide. However, if we consider non-axisymmetric solutions on extremal Kerr, what is the situation in this case? There has been a very recent paper by Sassels, Gralla, and Zimmerman demonstrating the behavior of solutions with fixed azimuthal frequency. So for such solutions on extremal Kerr, you have that the transversal derivative not only does not decay, but in fact grows like the square root of time parameter. Previously, for axisymmetric solutions, you have that it converges to a non-zero constant. But in this case, for the non-axisymmetric solutions, you have that the first order derivative grows like the square root of time. That's a very interesting result. And this is for fixed azimuthal frequencies. Now, what remains, okay, so we understand what happens for axisymmetric solutions. We understand what happens for fixed azimuthal frequencies, which are non-zero. Now, what remains to understand a full solution to the wave equation on extremal Kerr is to understand the tail of the azimuthal frequency expansion. So in other words, to understand the limit as the azimuthal frequency goes to infinity. For this tail, there is no result in the physics or in the mathematics community. Nothing is known. And it's probably the most interesting regime that I am aware of. The growth in the fixed M case basically comes from the behavior of quasi-normal modes on extremal Kerr and the strong superedians that you have in this case. If you let M go to infinity, then not only you have strong superedians, which gives you information about the quasi-normal modes, but in fact you will also have that these quasi-normal modes are superedian, but also strongly trapped, in some sense of trapping that I don't have time to explain. So in the extremal Kerr, you have coupling of the superedians and trapping, in fact. And the limit as M goes to infinity, this behavior has not been understood at all. So the conjecture that we have is that the full solution psi to the wave equation, which contains the axisymmetric, non-axisymmetric, and like the fixed M and the limit as M goes to infinity, is that such a solution decays inverse logarithmically. And that would be a very surprising result if it's true, because that would be a case where you have logarithmic decay without having elliptic trapping, as it's in the case of the ADS spacetimes, and you only have asymptotically large spacetimes with just trapping and superedians. Okay, so this is a very interesting result to see in the future. So hopefully I convinced you that conservation laws play a role in understanding the evolution of scalar fields. So as a mathematician, I was interested in understanding more about these conservation laws. So we developed a theory that characterizes the general conditions that provide conservation laws on any null hypersurface. So given a null hypersurface, can you determine if you have a conservation law in the sense that we have described so far? So we developed a theory that characterizes all hypersurfaces that admit conservation laws, and also the same theory characterizes all conservation laws that such hypersurfaces can admit. Moreover, we have shown that these conservation laws in the general theory are the only obstruction to gluing data. So if we consider a solution from the, that is defined, a scalar field that's defined on an algebra surface, and it's defined in the region between S0 and SV1, and another scalar field that's defined in the region between SV1 and S1, then the question is, can you glue these two solutions to the wave equation? And the answer is yes, and the only obstruction to gluing is the existence, if they exist, of conservation laws. So these conservation laws we've been talking about also provide a geometric obstruction to a gluing construction. Okay, so the next step, which I would like to understand, is what is the mathematical analog of all the things that I have explained in this talk for the actual Einstein equations. And I believe there will be various interesting results to be discovered in this direction. Okay, thank you.
Thank you. Questions? Yes. Obvious question.
So in a realistic scenario, you would embed, I mean, the asymptotic boundary conditions in some cosmology. I mean, there would be, I mean, you can embed them in the standard model of cosmology where there is a cosmological constant, or you can embed them, I mean, any other cosmology. How could that affect in any way what you said?
So these results are for asymptotic flat spacetimes.
Right.
Which, as we understand, is for isolated systems. Now, in the cosmological case, the situation is completely different because the boundary exactly at infinity has completely different nature. So these estimates are completely different. You don't have this asymptotic.
So that was not investigated, you're saying?
This has been investigated, yes. So you have exponential decay in this case. And there has been a theory that describes the asymptotics. And in fact, there has been more work in the cosmological setting because, in some sense, from a mathematical point of view, it's slightly easier to understand, precisely because the scalar fields decay exponentially. Okay, so in this case, you have polynomial decay, which is much slower, and so understanding the nonlinear theory is more difficult. So in the cosmological case, there has been much more progress.
I have a question. So on one of your transparencies, you wrote, on one of your slides, you wrote memory charge. Is there some, there's some relation to the memory at Scry?
So I call it memory charge in the sense that it's something that is preserved. And
you weren't trying to draw an analogy to the gravitational memory?
You mean the memory effect? What exactly do you mean?
That's right.
Yeah. No.
Okay. And another question, what happens if you add an interaction to the scalar field? Does the charges are all no longer conserved, or?
So if you have a charged scalar field, you mean?
No, if you say add a phi cubed term, or phi squared. Okay, if it's not a free wave equation.
Yes. So you still have, so in the nonlinear, for nonlinear wave equations in general, you still have nonlinear analogs of this conservation law, so you still have these instabilities. So the qualitatively and quantitatively, the picture is similar.
I see, okay. Further questions? Okay, great. Thank you very much.
Thank you.
Okay, so thank you very much for the opportunity to give a talk at this very nice conference. So, so just looking at the title of my talk, you might think that I'm going to spend half the time talking about astrophysics and half talking about quantum gravity, but that's not true. I'll basically just talk about quantum gravity. But, well, sorry. but let me just spend one slide explaining, what's the connection to astrophysics and why it is important for us. So the Kerr CFT correspondence deals with the extreme or near extreme Kerr black hole. So that's the Kerr black hole, which is very close to this extremality bound. And and the connection to astrophysics is basically that this can be taken as a model for an actual realistic black hole. For example, Cygnus X1, which was, whose extremality parameter was shown to be over, or estimated to be over 0.95. Now, what's special about this black hole is, as actually Alejandra explained in her talk, is that, so they're asymptotically flat, but in the extremal limit, they develop a very long throat, which we're calling the near horizon extreme Kerr throat, or neck. And what the Kerr CFT correspondence is basically a proposal for quantum gravity in this neck region. And what I'll try to convince you of in this talk is that this is a really promising avenue for understanding quantum gravity in the real world. So this is what my talk will be about. But just before what I want to say is that it's really important, since we do care about doing quantum gravity in the real world. This astrophysics connection is very important for us, one. And the second comment that I wanted to make is that, if we forget about the quantum part of this Kerr CFT correspondence, there's actually also a non-trivial classical statement of Kerr CFT, which involves the presence of an infinite dimensional conformal symmetry in this throat, which is purely classical, and actually can have astrophysics applications. So this symmetry actually can allow one to write, to study analytically, for example, emissions from the near horizon region, or the behavior of the magnetosphere near the horizon of this sort of black hole, which is a program that has been, started by Strominger and collaborators in the past few years and seems successful. Okay, but this is all I'm going to say about astrophysics in this talk. So let me go to the quantum gravity part. So the plan is, first I'm going to give a very brief review of quantum gravity, or more precisely holography, and why it's difficult. Then I'll talk about the Kerr CFT correspondence and what works and what is puzzling about it. And then I'll talk about how one may try to resolve these puzzles by using string theory. And then I'll conclude. Okay. So let me start by reminding you or telling you what is quantum gravity. And in this talk, I'll take a very, a very limited point of view on quantum gravity. So basically, the starting point is this Bekenstein black hole entropy formula, area of the horizon divided by 4G Newton that Alejandra nicely reviewed, and which is a completely universal formula. And if one, okay, and another thing I want to say, so what this formula suggests is that the degrees of freedom of the black hole, they don't live in its volume, but rather can be thought of as living on the black hole surface. And then if you take this formula to, the implications of this formula to their bitter end, you end up with the conclusion that, any theory of quantum gravity has to be holographic, which means that if I have a theory of quantum gravity in d+1 dimension, it should be entirely rewritable in terms of a theory without gravity, so I'll call that a field theory, in 1 dimension less. And okay, so this sort of statement is very non-trivial, but also it defines quantum gravity in the sense that, as you well know, in the gravitational picture, there are all sorts of paradoxes, black hole information paradox. The advantage of writing down this field theory is that this is just usual quantum mechanics, so there's no paradox, and we can just call this our quantum theory of gravity, in the sense that it's dual to a 1 higher dimensional gravitational theory. Why would we believe that such an equality exists between theories, very different theories in different dimensions? It's because we have concrete examples of this thing happening. And so the best understood set of examples concern the so-called ADS-CFT correspondence. So here, if we have a gravitational, so theory of quantum gravity on anti-de Sitter spacetime, what this is a very nice hyperbolic spacetime. So this has a negative cosmological constant. This can be shown to be exactly equivalent to a conformal field theory, which is a very nice type of quantum field theory. It's invariant under zooming in and out in 1 dimension less. And why do we believe this correspondence to be true? Well, first and foremost, string theory provides a whole plethora of concrete examples where things can be computed on both sides, and you always get equality. So this is our reason for trusting this correspondence. But besides these concrete examples, one can also make some sort of universal statements that any theory of quantum gravity on ADS, be it string theory or not, if you can find an example, should be dual to a conformal field theory. And there are certain things that universally have to match. For example, the symmetries on the two sides. In D equals to, the entropy should always match, but we can only compute it on the field theory side in D equal to 2. And there are the things such as quantum entanglement in the CFT has to do with the emergence of gravity in this picture, and some other consistency condition is dual to bulk locality. So on one side, we have these concrete examples that make us believe the duality, but also we have all of these universal features that are also interesting and true. Okay, so this is all very nice, but we should remember that we don't live in anti-de Sitter space, so how about quantum gravity in the real world? And okay, so let's just take, say, flat space. What is quantum gravity on flat space? The problem is that we really don't have much clue what the dual field theory should be. And the reason has something to do with something funny about our current way of understanding holography is that it's incredibly background dependent. So if I'm in ADS, we really have all these results and we understand things very well. The moment that I change the asymptotic background, suddenly we completely lose track of what's happening. So this question is quite hard to do it for the real world. And of course, people can try to infer. So what you can do, you can use these universal features that I mentioned before, and compute them on the gravity side and try to infer what the field theory in this question mark region, what its properties have to be. So you can look at the symmetries, you can look at the correlative functions, and so on. But the problem is that it's quite likely that whatever field theory lives here is non-local, and we have very little knowledge generally about non-local quantum field theory, so it's very hard to guess a theory if you don't have many examples. So from my point of view, this is my personal perspective, but I think this, this might be the reason that this issue is sort of hard. Okay, so much about quantum gravity in the real world. So now I'm going to try to tell you about the Kerr CFT correspondence and how the situation is significantly better in that case. Okay, so the Kerr CFT correspondence. So as I said, one looks at the extreme Kerr black hole, which has this very long neck region. And the conjecture is that quantum gravity, I forgot to say that we just chop off the asymptotic spacetime because the physics decouple. So the conjecture is that quantum gravity in this neck region is holographically dual to a two-dimensional conformal field theory. And the reason that we made this conjecture is basically, so I should explain. So in this neck region, so there's this azimuthal angle symmetry. I'm going to call it phi. And the next rod is infinitely long, so it has some sort of scaling symmetries. And what we found is actually we can do arbitrary phi-dependent rescalings, and that's still a symmetry. So we find an infinite number of symmetries parameterized by this arbitrary function, and the algebra of these symmetries is the so-called Virasoro algebra. Then you go and look and just try to guess, what sort of field theory has a Virasoro symmetry that's very constrained. It's infinite dimensional, so that should be a 2D CFT. And then we can check that, if we compute the entropy here, it exactly matches the entropy on the gravity side. So it seems like our guess is correct. And then there was a lot of work done, and it was shown that this sort of Kerr CFT reasoning is universal in the sense that it applies to all possible extremal black holes, also in higher dimensions with different charges and so on. And also a lot of additional checks of this duality. So for example, it was shown that scattering amplitudes match. More recently, in certain cases, it was shown that the entanglement entropy matches. That's a well more refined measure than the thermal entropy here. So okay, so this looks, this looks very successful. But what's sort of bizarre about it, everything that I've said so far, it also happens in the ADS CFT correspondence for ADS3 CFT2. And this is somewhat puzzling because, the next spacetime is not identical to ADS3, so why should we get the same sort of things? If you want to have a sort of picture of what NEC looks like, it bears the same relationship to ADS3 that a square sphere bears to the round sphere. So they're clearly not the same spacetime, so why do they look so similar? And so the question, what is the difference between these two? And it turns out that the difference is that if you look carefully enough at the spectrum of perturbations of the spacetime, you find that the dual theory should actually be somehow non-local. And okay, so there's some theory that has all of these nice properties, but should additionally somehow incorporate some sort of non-locality. What is this? Have we seen this before? That's sort of the question. It seems to be a new kind of theory. And for lack of a better name, I'm just going to call it a dipole CFT, something that has all of these properties. OK, so now the question is to define these dipole CFTs. And now we're really happy that we have string theory to help us understand what this might be. So string theory helps here in two ways. First, because it's a very rich, so it has 10 dimensions and all that. It has a lot of extra fields, a very rich structure, but it's very constrained. And also because it might provide us with some concrete examples, just like we had in ADS-CFT. So we can use first this rich structure to basically make some analog of the Kerr black hole that has many tunable parameters. And then by tuning them just in the right way, we can come to a limit where you can see that actually Kerr CFT is a deformation of ADS3 CFT2. And this might sound trivial, but it's actually extremely important because now we have some sort of tunable parameter that allows us, when it's 0, we're in the very well-known case of ADS3 CFT2. When we make it non-zero, we're in the regime of Kerr CFT, but we can really do perturbation theory in this parameter. So that's important. And just having, so it turns out that the deformation looks irrelevant. It's not the favorite kind of deformation that you want to do, but such is life. And such a deformation actually would immediately lead to a non-local theory. So this clicks well with this intuition. However, it's very confusing before doing an actual calculation to see why the entropy and the symmetries would be preserved. So that's still a puzzle. And in order to address that puzzle, actually, we can again use string theory to look for some more inspiration. And actually, what we can find are some sort of higher dimensional generalizations of Kerr CFT. So these theories, they again have sort of CFT-like entropy and this sort of similar kind of spectrum, but they don't have the Virasoro algebra because Virasoro is something very two-dimensional and doesn't exist in higher dimensions. And it turns out that if we search the string theory literature enough, we can actually find an example of a theory that does exactly what we want. So this theory is called the null dipole deform n equal to 4 SUN super Young-Mills theory. It's a four-dimensional theory. So this n equal to 4 SUN super Young-Mills is actually an incredibly well-studied example of CFT, and the ADS-CFT correspondence is incredibly well understood for it. And this is some particular non-local deformation of it that was written down by Bergman and Ganor in the 2000s. And what's interesting about this deformation, so it makes the theory non-local, but somehow this, I'll be done in just 1 second, by some sort of irrelevant operator, just like here. But this irrelevant operator is incredibly special, and in the end, the entropy is preserved. So this sounds like the right kind of theory that we want to look at. And then it turns out that actually this theory is integrable. So integrability is a property of n equal to 4 super Young-Mills, and the deformation preserves it. And if the theory is integrable, we can basically compute the spectrum using some very powerful techniques, which is something I'm currently doing with my colleagues in Artita. So, okay, so we actually have, powerful an example and powerful techniques to study these theories. Okay, so just to conclude, so I try to tell you that, quantum gravity or holography for realistic backgrounds is hard. However, the Kerr CFT correspondence might be, an interesting avenue to explore. First, because it can be applied to actual astrophysical black holes, so it's realistic. And also importantly, because it may actually be tractable. And the first point is that it's a deformation of ADS CFT that we understand, and in principle we can track down. We don't have that for flat space. And we have this tractable, this explicit example, the dipole deform n equal to 4. And the hope is that by really studying all of this, we might come up with a whole new class of non-local quantum field theories that are dual to extremal black holes. And if we get a general definition of them, maybe we can understand holography in more general space-time, including flat space. Okay, thank you.
Questions? Andrea?
So if I remember correctly, there were some proposals for flat space holography by De Tournay and Camilla a few years ago. Do you have any comments on that?
I don't know it.
Okay. We can discuss offline.
Okay.
Gaston?
I'm just curious about this operator, the Bergman-Conner operator that preserves the entropy. This irrelevant operator, how it look like, or you have a family, or there is some parameters, how natural it is?
Yeah, so basically this dipole deformation, what you do, you take the n equal to 4 Lagrangian. So this is a weak coupling. And you replace all products by a certain star product, which is non-local. And when you rewrite the star product in terms of the usual fields in n equal to 4, you get a bunch of, just higher dimension, higher spin operators, an infinite series of them at weak coupling. And their coefficients are tuned in a very particular way. However, the properties, if you just use the star product and do Feynman diagrams with the star product, you find that planar diagrams are, with no external legs, are identical with those in the n equal to 4 super-Young mills. So this is what's telling you that the entropy is preserved.
Is that just a large n result, or is that?
Yeah, it's planar. Yeah, 1 over n does not hold.
Okay. If there are no more questions, let's thank all the speakers.